Good morning, everybody. Today, I would like to show you some results of a modeling activity that we are doing in order to characterize the geomechanical behavior of the shallow subsurface. In particular, we are trying to reproduce a loading experiment, an in-situ loading experiment that we carried out in a natural marsh in the Venice Lagoon, particularly in Lazzaretto Nuovo. Lazzaretto Nuovo is a lagoon sector located approximately 5 kilometers northwest from the historical center of Venice. And as any other transitional environment, now is threatened by various factors, such as the rise of the sea level and the land subsidence. In general, the Venice Lagoon, and so the city of Venice and the lagoon, is a critical coastal area because it has a peculiar morphological settings under some specific meteorological condition. The lagoon is submerged. It can be partially or totally submerged because there is a large inflow of water coming from these three inlets. So with subsidence and the sea level rise, this condition can be worsened in the future. If you look at this subsidence map, you can see that there is a large variability of subsidence, with subsidence rates that can go from small uplift to a maximum subsidence of 20 millimeters per year. And we can say that in the north of the Venice Lagoon, the average subsidence could go from 3 to 4 millimeters per year. Then the central part is about 2 millimeters, and the southerns is 2-3 millimeters. What we are doing is trying to study the shallow component of land subsidence, which is autocompaction. And for anyone who doesn't know, autocompaction is a soil loss, elevation loss, due to consolidation of sediments due to their own weight. We are trying to do that by means of this loading experiment that we designed in order to characterize the soil compressibility of this shallow environment. And this was a great opportunity because for the first time, we studied autocompaction in undisturbed field conditions under a controlled force of stress. And this is important because in this way we can really study the long-term natural consolidation that can happen after sediment aggradation. And we can do this with a test of few days. And the other important thing is that the test resembles the standard odometric test, but it is done in field conditions. And this is important because it helps overcoming the main challenges of indirect evaluation, which could be from the sampling of the loose soil or soil heterogeneities, because it is done, the load is distributed in a greater area respect to a laboratory test. Regarding the setup of the experiment, we are using these blue boxes. There are tanks of 500 liters, and they're done in polyethylene. And the boxes are filled with seawater that are coming from the nearest lagoonal creek, and they are reaching a cumulative load of 14 kilonewton in an area of about 4 square meters. The experiment, these tanks rest on a reinforced geotextile and on 4 wooden pallets, and this is needed in order to redistribute the load on the area, and also to eliminate or at least reduce the buoyancy forces that are coming when the high tide is rising, when the tide is rising. The experiment is composed of 3 loading and 3 unloading stages with different duration and different load densities to characterize the geomechanical properties in virgin loading, unloading, and secondary compression conditions. Here you can notice that the second stage was repeated here, because there was a big storm that partially ruined the instrumentation. So for the sake of the modeling activity, we just focus on stage 3 because it resulted to be the more stable, consistent, and less disturbed by external factors. The experiment was equipped by a suitable set of sensors that measure displacement and vertical displacement and groundwater pressure. If we look at this figure, we can see that there are this one, that there are 5 displacement transducers. 3 of them are located at the center of the loading area, at the surface, 10 centimeter depth and 50 centimeters depth. One is located on the external part of the loading area, and the other one in an intermediate position at 10 centimeters. And the sensor position is designed in a way that we could catch the entire shape of the formation with expecting greater deformation in the middle of the loading area. Instead, if we look at the pressure transducer, they are more or less they have a similar configuration. They are just positioned in an orthogonal direction respect to the displacement transducer. So here you can see that there are two in the middle. So there are external sensors and intermediate sensors. What we found out with this sensor, is that the maximum displacement, the maximum settlement here is of about 7 millimeters for the sensor positioned at the middle of the loading area and the surface. For the one positioned at 50 centimeters, the maximum settlement is about 2.5 millimeters. Instead, for the external one is about 0.7, sorry. And another thing that it is visible is the creep behavior, the one due to the viscous deformation, because here from this point you can see that there is an increase of slope. So we maintained the load for more than 20 hours. For this reason, it was possible to actually see this viscous deformation. And another important thing is the rebound. So after the final load release, which is about 3 to 4 millimeters, which is about 50 to 60% of the maximum deformation. If we look instead at the recorded time series in terms of pore pressure, we can see that the biggest peaks here are not really given by the load that we were giving, but it was due for the tide. So the biggest peaks are given by the tide. Instead, these smaller peaks that are smaller and shorter are given by our loading here and our unloading instead here. We try to reproduce these measurements through a Poro-mechanical model, which uses standard finite elements for displacement and mixed finite elements for pressures. So basically, the model solves the flow and the structural equations. In order to give vertical displacement, groundwater pressure, and flow. And moreover, we implemented an hypoplastic constitutive law in order to take into account the change of stiffness with the loading and unloading cycles. We found from a standard odometric test that the shape of our constitutive law is parabolic. So here the stiffness increases with increasing of the effective stress. And as initial parameters, we use estimation given by actually the laboratory testing. The simulated domain is a part of the lagoon, and the setup, the mesh follows the setup of the experiment. We can see that the computational mesh decreases, the size of the computational mesh decreases going toward the center of the loading area and in the first 2 meters under the subsurface. Also, the buildup of the subsurface reflects the lithological sequence that we can find in that area. and we can have the first 20 centimeters of pit layer that overlies a 6 meter silty soil layer. And these two layers in particular are simulated with the nonlinear soil compressibility versus effective stress constitutive law. Instead, we simulated also the system of wooden pallets and geotextile with a linear elastic constitutive law where the soil is a prescribed value. And same with the linear elastic constitutive law, we simulated this deeper and stiffer layer. And what we did was calibrating actually the constitutive law and the hydraulic permeability in order to match with the pressure. And here I can show you how the idea behind the model. So basically, when the load is applied, displacement starts growing as well as the pore pressure, also here. And here the pore pressure starts dissipating while the displacement continues growing. Here you can see that there is a small reduction in the displacement and also in the pore pressure. It was because because of the high tide, the submerged part of the equipment. And here we continue seeing the displacement that are growing and the pore pressure that is dissipating until the end, where the final load is released and the displacement reduces and for the final rebound, and the pore pressure continue dissipating. Here you can see a more direct comparison from of the experimental data with the modeling data. One thing to notice is that the model cannot reproduce the creep behavior yet, so we are working on that. And so we remove the creep. 3 minutes today. We remove the creep, the part of the deformation given by the creep from the measured data in order to have a more visual, a more comparable displacement. And here you can see that actually the dynamics of the dynamics is well captured. Also, the part of the rebound is pretty much captured, and this means that the constitutive law that we have chosen actually works. And also we can see this. If we look at the pore pressure, this is a little less straightforward to understand because the tide here plays an important role. In fact, as I was saying before, the measured pore pressure are really influenced by the tide. But if we look at the two sub-panels that that are the one related to our loading, we can see the dynamics and the order of magnitude is captured, and it is about 3 centimeters of water column. So to summarize, we performed this original in-situ loading test in Lazzaretto Nuovo to characterize the compressibility of these shallow soils. We replicated the measurement through our model, and we can say that the heterogeneity of the soil is satisfactorily represented because both the computed superficial and intermediate displacement actually reproduce the recorded data. And also we can say our calibrated hypoplastic constitutive law can satisfactorily capture the recorded movements. This modeling activity is useful because the calibrated compressibilities then will be used for long-term modeling of the lagoon evolution. And also, last thing, we are still conducting poro-mechanical modeling of other in-situ loading tests that has been performed during the last years. We have this one, so in Lazzaretto Nuovo, performed in 2019. 2020, we performed the test in La Grisa. 2021 in Campalto, and finally last year at Saline. And also only from the field experiment we can see that there is a really range of variability between the maximum displacement, so we are really looking forward to see what the modeling actually will tell us. So thank you for your attention.
Thank you for the interesting presentation. So, there is the question.
Thank you very much. Really nice experiment. I think the experiment would be even more richer if you would have installed an extensometer or a pressure device vertically to connect actually the results to the formations, so the different layers. Have you considered that? So to vertically to measure actually the strain for the different formation with an extensometer.
So actually, I'm not the designer of the
Okay.
the experiment, but for sure there was a lot of thinking behind it, and yeah, I think that all the consideration has been done. So I'm not. I think I'm not the right person.
Very much for the presentation. My question is related to the characterization of your natural soils. I mean, to calibrate the parameters of your model, did you collect samples or perform in-situ investigation to give an interpretation of the geotechnical compressibility?
Yes, they collected some samples, and laboratory testing then told us with laboratory testing, then we started from there for our calibration. So the initial parameters are coming from the metric test actually performed in laboratory.
Okay, last question, please.
Thanks. It's really nice. I mean, I really like this experiment, but I'm curious to know two things. What is the effect of the strain rate, you think, on your experiment? Because you apply this load on the compressibility afterward. Yes, and the other one is about the calibration. How did you do the calibration?
So I'm starting with the second one. Calibration is done by trial and error. So we are starting with some parameters from geotechnical laboratory testing, and then we trial and error. We're trying to match the measurement that they did. For the first question, I don't think I really got it.
It's about the time of loading, I think. I had the same question. Did you load your soils in an instant, or you load it little by little?
No, so in these experiments, the loading were about half an hour, and then the load was maintained for more than 20 hours, I think 22 or more or less, something like that. And then the unfill, it was as well in 1 hour and a half.
Okay, thank you very much, Selena, for your nice